Good afternoon. Thank you for joining I²CNER seminar series. I'm Yoshinori Sawai from Department of Mechanical Engineering, Faculty of Engineering. I will be host this today's seminar. And in I²CNER, I belong to the Advanced Energy Materials Shaft and working on the tribology research. Maybe some of you are not familiar with the word tribology, but the tribology is the research about friction wear and the lubrication. So today I'm very excited because we could invite a very distinguished researcher in the tribology field, Professor Hitoshi Washizu. And I would like to introduce Professor Washizu briefly. Professor Washizu is a professor in Graduate School of Simulation Study at the University of Hyogo, and he graduated from the Tokyo Institute of Technology and got a bachelor degree in 1996. Then he entered the Graduate School of University of Tokyo and got a PhD in 2001. And his doctor thesis was about molecular simulation of polymer solution at the physical chemical laboratories. And after he got a PhD, he joined the Toyota Central R&D Labs and started his career as a tribologist. Tribologist means that researcher in the tribology field. And then, after several years in industries, he moved to the University of Hyogo in 2015 as a professor. And he has been working on the simulation, mainly a molecular dynamic simulation about the friction and wear of material and also the lubrications. And today, I asked him to conduct same lecture entitled Multiscale Simulation of Friction and Wear. And before start his talk, I would like to take a moment to remind you that your questions will be addressed after the presentation. And please use a raise hand button or type your comment in the Q&A box. When you are called on, please unmute yourself. And also, I would like to remind you that this webinar will be recorded and made available on the I²CNER website later. So now, everyone, please welcome Professor Washizu. じゃあ、鷲津先生、お願いします。
Thank you very much for a very nice introduction. And yes, and it's my great pleasure to have an opportunity to make a presentation in this great laboratory. And so my name is Hitoshi Washizu, came from, now we are in the Hyogo. Now I'm coming in Himeji City, not in the Kobe city, but anyway, I'm making talk from the Hyogo prefecture. And today I'd like to talk about the multiscale simulation of friction and wear. And as the Professor Sawai sensei said, not all of you are familiar in tribology. So I'd like to explain from our very basic research to the applications. So let's start. And but before then, I have to introduce about the prefecture of Hyogo. And Hyogo prefecture locates here. So if you want to go from north end to the south end of the Honshu, you have to pass Hyogo prefecture. And yes, and the second one is that last year, 2023, ITC means International Tribology Conference was held in your city, Fukuoka, and it was very great conference. But in here, we presented several 23 presentation here because the reason why is that we have many laboratory here in the Himeji is School of Engineering and one laboratory in the School of Science, and I belong to the information science. So and we are doing the tribology. So in the Hyogo University of Hyogo, we have many tribologists. And here, our university locates in the island, so artificial island named Port Island. And here is the locates the next generation's supercomputer named Fugaku. And was the top in the 500 in the supercomputation in 2021 and 22. And now it's fourth or fifth in the world. So it's like a very capital of the supercomputing in the world. And we also have a small supercomputer in our university, and there's focus is some organization which makes service to the engineering some commercial engineers to use the supercomputers. So in this area, we have many supercomputing person, and we are doing the research here. And in our university, we are educating too. And so we have, this is my figure of my laboratory. And we have, the reason why I make this picture is there's too many PhD students from the industry. So here's the name of the corporation. So so many people are interested in doing tribology or surface science simulation from the molecular level. And we also have master course students, and we have collaborators. And yes, here's one of my strong collaborator is I²CNER University. And so, okay. So we are doing the mesoscale simulation to the nanoscale simulation. And now the very hot region, very hot field for the material simulation is the simulation technique from the bottom up in the quantum level to the atomistic level. And here's many research here. But our main research interest is in much more coarse grain here, a coarse grain model. This is that here's the atomistic model, and here's a coarse grain model. And but in this coarse graining method, there is no unique established technique. So we have to make. For example, I will tell much more precisely later that collaboration of the molecular motion and fluid dynamics is one topic. And this is a very hot topic for us because it has many industrial applications. All right. But anyway, for the mechanical engineering point of view, the continuum model is a much more basic and much more well-established method. Like this is lattice Boltzmann method, but maybe you may know other FEM or finite element method or so on. But we are doing the simulation, making simulation from the millimeter level to the atomistic level based on the particle simulation. This is our feature of my laboratory. Okay. So let's go on. And we are not doing not only about the friction, but so for example, we are doing the liquid crystal or surface coating polymers. Maybe I²CNER University is one of very famous. And we are also doing the material informatics. But the main is molecular dynamics, okay? And the main technique is the molecular dynamics. And if you don't know, if you're an experimental researcher, I will explain about this briefly. We solve the equation of motion in the classical Newton equation of motion. And this means that F equals m times A. A is acceleration. And so this F is named in our field, this is named force field. Okay, and we solve the equation of motion of the atoms. Okay, and if the force field is realistic, the motion of the atom becomes realistic. And we have the force field is a set of the formula, and it is one of them are bond and between two atoms, and angle between three atoms, and torsion means that if there are three atoms, we make one plane, and so we can simulates the torsion. And for the organic molecules, torsion is very important. And also important is the van der Waals and Coulomb interaction, because Coulomb interaction is on the molecules. So electrons exist in some space or some, so the molecular charge or something. So it is localized. So localized atoms between the two localized atoms, we should calculate the Coulomb interaction more precisely. Okay, so we put these set of the equations to the force field as a parameters, and so the parameters are usually calculated from the much more precise quantum simulation. Okay, so and for example, I said partial charge is important. So for example, we made some new technique to simulate some liquid crystal molecules. And here's the liquid crystal part, and here's the ionic liquid part, and these are combined. And so in the experimental point of view, Professor Kato in the University of Tokyo made this kind of molecules, and it makes a self-organized structure like a 3D or 1D, quasi 1D, and but it's difficult to simulate by the computer simulation. So we made a modification of the technique to assign the partial charge in each atoms. Okay, and because these are ionic moiety has a very strong. So in the gas phase, they have -1 and +1 electrons. Okay, but in the condensed phase, it's not true because the electrons goes out elsewhere. Okay, the other environment. So at first we calculate by molecular dynamic simulation +1 and -1, and then so make a relaxation process, and then we get some new configuration, and then we do the quantum simulation. Okay, and assign the new partial charge in each atoms, and then finally we can get a stable partial charge. After that, we simulate the much more larger systems like this and this, and then we can reproduce the structure, okay, of the 3D dimensional or one-dimensional system. Okay, and we put some water, and then we could separate and distinguish there are 4 types of water in the thermal or stochastic mechanically, and we can distinguish these atoms. Okay, so this is some of my example of our new technique to make the new method to calculate the molecular dynamics. And the other hand is that so how to understand the results obtained from the molecular dynamics. Okay, usually this kind of soft materials, we use some radio distribution functions. But in this kind of large polymer, this is some dielectric polymer. We use these kinds of polymer for the actuators, and we'd like to have a dielectric constant. But we need some large, so this is some computer simulation size of cell. We change the cell size, and the usual computer, we cannot make such a large simulation cell, but using the supercomputer named K, we can prepare very large system, and then we calculated the dielectric constant. And it was overestimated in the small cell, and then it goes to stable value. But after then, we'd like to understand what's happening in here and here, okay? But using the RDF, we cannot distinguish this structure. But using new method named persistent homology can distinguish like small cell size, large cell size. So this is aggregate and this is diffuse. And this is what the meaning of this picture is, okay, after the simulation, we get some position of each atoms, all right? And then we make the balloon, the yellow one, and then from each atom. And then at some time, it's time to, size of the balloon, we can make some figure. We can make some these four are touched together. Okay, and this is named a birth time. And then the space here, you can see the space. But after then, if we bloom, and then the space vanishes, so we call this a death time. And we put the birth time and the death time as a one plot. Okay, and this kind of very complex structure, we have many plots. Okay, and then here's these are diffuse. Okay, and these are not, these are aggregate. And this is finds that the difference between the liquid and amorphous silicon. But this is, we found in the polymer solution. Okay. And this is some our results to understand the results of the molecular dynamics simulation. And this is a technique to simulate the atoms, okay, and how to understand, analyze the results. All right, so let's go to, so we are not not only doing the tribology, but after then, I'd like to talk about tribology much more. And here is so let's think about the origin of friction. So origin of friction is that, so I talk to the my students that, you know, superconductivity or super fluidity, there is some experimental evidence, and there are some well-established theory to understand these kind of super conductivity and so on. But super lubricity, there's no experimental evidence, and there's no very well-established theory. So if you are a theoretician or if you're an experimentalist, please do solve this problem, okay? So origin of friction is now still open question. But we know that, so if the two solid materials are faced together, so energy goes to upper side or lower side. So we call this heat dissipation. Okay, so we made this kind of model. This kind of model are discussed, of course, from very 1990s or so on, and many of them were used FKT or named PT model. This is the model is that there's very stiff surface, okay, and then there's only one layer of the atoms on the bound to the here. Okay, but we made that, but in the realistic, so I'm half a physicist and half a chemist. So I'd like to use a much more realistic system. And much more realistic is that in this case, we added a number of the atoms in the bulk side, okay? And then we calculated the friction. So what's happened? So, and we used a parameter for the diamond and spring constant and mass. And 10 meter per sec is a little bit slower, I mean, from the molecular point of view. But I was a part working in the automotive industry. So this is a realistic speed for the combustion engine. Okay, and we put this kind of parameters and then calculated this. And if there's only one single atom, the friction coefficient of friction is very low. This is because the bond is very stiff and bond parameter is high, so it is they do not move, so so energy dissipation cannot occur. But if we add some number of the atoms in the deep bulk side, 100, 300, and 1000, these are obtained by simulation, okay? And this infinite value is calculated by Dr. Kajita-kun, and he was very young, and he did a very good theoretical effort. And then he calculated here infinite, and the simulation value of the 1000 and the infinite is also same. All right. So this means that the origin of friction is a phonon vibration in the bulk. And about 1000. Of course, this depends on the material, but for example, for the diamond, it's 1000. So the origin of the friction is due to the phonon dissipation into the bulk atoms. Okay, so this is, and the theory of the super lubricity is that the pitch of the atoms are one by one. This means that here's a potential barrier here, and then every atom climbs a barrier, and then climbs a barrier, and then an atom vibrates, and then heat dissipates in the bulk. So this is a mechanism. But if we put the pitch about the 1 by root 2, okay, 1.41, like so that some atoms climb the potential barrier, and some obtain some force because they descend the potential barrier, and then some of them are top. So Professor Hirano made some concept of the super lubricity in the if the we call this situation incommensurate. Incommensurate state, the friction vanishes, he said. But if the one atom hits some other atom, so energy dissipation occurs. But because of the force in our some goes this way and this way, so cancels. So the friction force, the absolute value descends, but there's still there. In theoretically, there's no vanish in the friction force. There exists, okay. But in practice, we use some this kind of material named layered material, okay. And here's, we made some model, but to compare with the experiments, these are too large. So like this one, so we need to coarse grain the model. So coarse grain to 1 seat, and then, so this can enable to simulate a huge amount of atoms in one. But we introduced a translational degree of freedom and rotational degree of freedom, because in incommensurate states, it is not like this, okay? So, and also the interaction between seats are calculated very precisely for the potential parameter. And then we put some, do the sliding friction, okay? And this mountain is some potential barrier between this red lowest sheet and the disk, okay? And we have 10 layer. And on the upper side of the 10 layer, we have another one which slides in constant velocity. Okay, so let's do the simulation. Oh, sorry. Let's do the simulation. And then you can see that, there are thermal vibration. Okay, so after the sliding, it goes straight, but it's not incommensurate, it's commensurate. But, you can see that here, this most lower sheet is sliding like this, like dancing, okay? It's not a simple interlayer slip. Let's see from the upper side. And then you can see this is the top of the mountain, potential barrier. And then, but after the simulation, it goes to this line. This line is that this valley of the potential barrier, and it's almost plane. So this is a potential. So the force becomes escapes in the potential barrier, and it becomes very, very low friction. So this is the reason why this kind of like a graphene makes very low friction. And we named this is supported by the thermal fluctuation. So I named this phenomena as a thermal escape motion. And this occurs in the commensurate system. Yeah. So I believe that this can be solved by other experiments, but it is still open question. So my paper is more than 10 years old before, but not so many referred. But I think this is very important for explain very mechanisms of the low friction. And one realistic thing is that in the realistic system there's water molecules in the atmosphere. So we also simulated much more precisely, and this model is all atoms molecular dynamics simulation. So last figure was the coarse grain model, and this is much more realistic model. So we can confirm the realistic truth of the coarse grain simulation by much more smaller simulation. And we can include some chemical effects, such as the effect of the water molecules. All right, so this is one example for our basic research to understand the friction. But today I'd like to explain the latter part of this my talk. I'd like to explain about much more coarse grain simulation for the fluid and the solid. And so let's go out from the molecular dynamics. But first, we can confirm that what we can do for the using the classical molecular dynamics. And this is one example for the organic monolayer here. And the organic monolayer is this green molecules, and then it has some polar part, and then it interacts with the surface by Coulomb interaction. And I told my student to do this simulation, but he said, so this do not absorb on the surface because here it touched down. Because so this means that the blue molecules are the solvent, hexadecaine, and so structure. So additives, number of the additives are too small for the realistic system. So the solvent makes some absorbed layer here. Okay, so the absorption time depends on the structure of the base oil. So this is very new finding in our simulation for the organic monolayer. Okay, and so absorption time depends on the oil, like this and this and this are different. Okay. And now, so this is classical molecular dynamics. So what can be do? But some experimentalists says that there are many chemical reactions on the surface. So we extended this to incorporate the chemical reaction. But chemical reaction, to treat a chemical reaction in a molecular dynamic simulation is very difficult because the number of the elements, if the number of the elements grew up and becomes larger, the simulation becomes much more difficult because we have to prepare the potential parameter. So in this new concept of the potential is the neural network potential. That this means that so if there's some configuration of the atoms, then they calculate the potential energy. Okay, and they did the 10 million DFT, there's no functional theory calculation, and then they put some figure like this, potential energy figure, and then they introduce many kinds of elements here, and then, but these data are discrete, okay? But so we need some in order to calculate the force, we need to have a difference. So we use the neural network to calculate the force, and every time we calculate the force, we suspect the force by neural network, and then calculate this. Here, there's a zinc DTP and MODTC, so there are many kinds of elements, but the surface chemical reaction, like zinc molecule atoms face together, like such a kind of, they are condensed here in the surface. This is experimentally known, but we can simulate this from the dynamic simulation. So I think this is very useful for understanding some new, we called tribal chemical reaction. Yeah, using here. But another thing is that this is very basic concept of the Bowden table, and so oiliness, oiliness improver is like a fatty acid, which I previously showed, and this works here, and these kind of additives work on the low temperature. Okay, and there are another kind of additives named EP additives. This is anti-wear additives, and this is but these additives do not work on the low temperature. Why is this? And these have phosphate on this has carbonate. Okay, carbonate works on the low temperature, and phosphate works on the high temperature. What's the difference? So we calculated this. We prepared the phosphate molecules in the base oil, and then we found that they make aggregates. So it depends on the molecular structure, but they make aggregates. And then so the size of the aggregates depends on the some additive molecular structure. And then so in the low temperature, they are very stable in the oil. So they do not reach to the surface because this is the particle size, and this is a diffusion coefficient, and diffusion is very larger by compared with a single molecules. Okay, so the surface interactions becomes rare in these kind of phosphate. So I'd like to express that so we can distinguish the difference between the chemical structure on the many side. Okay, but maybe you may understand. So here's okay, another example. This is some lithium ion. It is we call thickener in the grease. So grease, so grease is getting much more important because nowadays we use the EVs, and so lubrication for the electric vehicle we use grease. And this is one kind of grease, and this is another kind of grease. And the difference is that we have OH side, only here, and there's not OH, but the stable structure is very different, like this and this. And in this case, so in this case, the structure is much more selected, and they are separated. But here, the aggregation combines together. Okay, so these kind of difference can be explained by how to share the lithium ion on the organic system. And then, so here's this is the OH group, and so this is the end group, and the OH group interacts between the lithium ion, so the aggregates becomes larger. And this kind of phenomena is confirmed by experiments. Okay. But yes, but so here's another thickener named this urea grease, and the center of the thickener is same, but the some branch is different, like a circle one and aromatic one, and this kind of other one. And so the structure of the aggregates is different. And this kind of these difference can be explained by the hydrogen bond. Hydrogen bond is a bond between the OH group and the others, but here we have many charged part, so and hydrogen part, so they make some interaction, and so this kind of difference occurs. Okay. So using the molecular dynamics simulation, it is very useful to understand we can explain many phenomena in the world of the chemistry. Okay, so it is very useful. But from the mechanical engineering point of view, we cannot explain this kind of fiber structure or much more larger structure by the chemistry. Because the micelle, the very small partial structure of the micelle is reproduced by this kind of molecular dynamic simulation, but this kind of fiber structure cannot be treated. So we used dissipative particle dynamics to make some model of the this kind of thickness. All right, so and in this dissipative particle dynamics, so we coarse grain the model to like this. So we have many atoms here and many atoms here for the base oil and the thickener, but we coarse grain to the only three sphere, and with this like only two sphere. And then so equation of motion, we include dissipative force and random force because there's thermal vibration here. So we have to introduce this kind of thermal effect. Okay, and then we can calculate this. And here's a no share structure. They make a self-organization structure, and then if we add some share, and we can get this kind of structure, and then under high share, this kind of micelles breaks down, and then we can obtain the viscosity, and the viscosity curve decreases with the first regime. And the first regime is a rotation of the this kind of micelles, fiber of the micelles, and then it becomes like this, and then get some plateau value, and then much more higher share, and then this structure of the micelles breaks down. So this is very these kinds of rheology curve is obtained by experiments, and we can model this what's happening on this kind of situation. So it seems it is impressive. Yeah, but much more precisely saying, so structure of this micelles is not equal to a structure of this micelles. So we need much more precise, precise but large space simulations. So let's go back to the DPD. So DPD is like this, and then so we calculate the motion of the equation of motion of solvents and solute both. And so so the share can be adapted easily, and it is very good. And the multiple coarse grain system in the Brownian dynamics like this. But so we do not introduce the motion of the solvents directly. So the calculation cost is low, but it is not precise. So we made some new simulation that we couple the Brownian dynamics with lattice-Boltzmann. And then here's the concept is that we put some Brownian particle as a point charge, a point mass, and then calculate the force. Here's a force, and here's a force of the using the Navier-Stokes equation. Okay, and so. And here, so we can introduce some fluid dynamic effect much more correctly. And then here's some velocity autocorrelation function. And if there's not fluid effect, so this green line is that hydrodynamics effect. So this is a correlation between the velocity. Okay, here's some velocity, and then here's another. Okay, here's some velocity, and then if there's velocity, there are solvents. So the solvents goes this way, and then but they have Brownian motion, so they go to another side, and then so they forgot about the initial velocity. Okay, this is this green line. But if there is the hydrodynamic force, so then the solvent, I mean the base oil, remembers this, and then they tells to the particle that, oh, you are going this way. So the velocity correlation after the seconds, they do so they remember. So this is named long time tail or memory effect, and this is correctly calculated. This means that the effect of the hydrodynamic force is calculated correctly. Okay, so we could combine this. So this is some example for the share. And then here, in the static condition, the diffusion coefficient, sorry, this mean square of displacement is depends on the T, but here the T cubic in the share condition, this is named abnormal diffusion, and we could reproduce this and so on. And one application to the oil is that viscosity index improver. And so I thought I was working in the automotive industry, so so the oil have a temperature, the viscosity of oil has temperature dependence. Usually, the viscosity decreases with the temperature increases. This means that in the beginning, so we use a very low viscosity oil to improve the efficiency, but in here, so this is in the winter, so yesterday I was in Fukuoka, and it is very low cold temperature. And then in the cold temperature, is viscosity becomes lower, so it's very good. But after you put some engine, and then heat generates, and then temperature rises, and then this viscosity is too short to make the lubrication film in the engine. So we put some polymer here. In the polymer, in the low temperature, it is very small, but in the high temperature, it becomes larger due to the thermal effect. So we can improve the viscosity, makes flat dependence of the temperature. So this is named viscosity index improver. What's happening is that using this simulator later, it is very easy to in the static condition and on the shear condition. Okay, let's see. In the static condition, there's no shear, and so a radius of gyration, so size of the polymer is larger in the high temperature. Okay, but in the shear condition, it is different. In the high temperature, it is low. What's happening here? So this is X component. X means direction of the shear. So in the low temperature, viscosity of the oil is high. So the polymers is stretched in this direction. So in the making some figures, it's like this, that in the low shear rate, so the low shear rate polymers blooms up, then viscosity rises, and then so we can make some large we can keep the oil film. Okay, in the high shear rate, in the middle, and the shear rate is high, so you don't need to enhance the viscosity. But here, so the polymers is stretched, so this do not affect on the viscosity rising in the whole oil. So this effect was not explained, but by some simulation, not by simulation or by the experiment. So our simulation first explained this effect. Okay, so there are many applications, but so we introduced some effect of the some charges, and this is a difference between dipole and non-dipole model. And then so the structure of the polymer changes. This means that we can make some much more precise chemistry in this model. So this is very good. We are collaborators at a chemical company, Mitsui Kagaku, and we are so we could explain which kind of friction modifier is polymers are good for the in the dipole, I mean the polar system and the non-polar system. Okay, and this is we extended this to the this is some proteins, and but I don't think I have enough time, so I don't explain. But the structure of the so polymer is different under the shear. This means that so some biological effect is different in the depends on the biological effect means that the structure, stable structure of the proteins is different in the low shear and high shear. And so if this can be related to the some biological effect, this is some I think we make new science in the biology, because protein folding is very important field in the biochemistry, but many of them are discussed in the static condition, but in the shear condition, like in the blood, we need to understand the effect of the shear. All right, so but so this is one simulator made in our laboratory, and this is the model is about beads and polar residues and proteins, and united atom model is also already done, and so one more thing is that so parallelization and so to the adoption of the GPU is very important. But yes, and we are using so we have some grants from the NIDO to the wind turbine project, and then we are extending to makes much more effect so much more you know good feature in our simulator of the fluid. So The reason why we need some good simulator is that in the molecular level it is precise and chemically it is right, but we need to coarse grain to understand what's happening in the much more larger region, like the grease or some polymers and or some aggregates and additives. So we made a tribal fluid simulator here. And the last part of my talk, I will explain about mesoscale tribal SPH simulator. And these tools are original technique, and these are basic technique. Okay. And so we use some particle simulator made by Makido Group in the weekend, and this is named FDPS. FDPS is the framework for developing a particle simulator. And the particle simulation, it's not so well established compared with the FEM or so, much more classical mechanical engineering technique. So, and they are they are doing the astronomic physics, like they are calculating galaxy and so on. And in the galaxy, there are many particles, and the interactions must be calculated correct, but there are too many particles. So to analyze mesoscale phenomena, we use the SPH is a smooth particle hydrodynamics method, but it's not only for the hydrodynamics, but we can do some simulation of the solids. And we use we made some simulator based on the FDPS because we located in the weekend. Okay, and here's one topic. Friction occurs like here, but if we'd like to understand not only the friction, but the wear or some destroy of the surface, like a scissoring and so on. So we need to simulate much more larger space. But by the molecular dynamics simulation, we can only treat only small space, and like a few nanometer or okay, if we use much more larger, like 10 nanometer, 30 nanometer, it's okay. It's very good molecular dynamics simulation. But tribology effect happens in much more larger system, like 1 millimeter or some sub-micro, sub-milli, like, and if we rub here in the very high by the metal and metal, it's only the heat generates and it's the temperature grow up and it ends. But at first, so we call this a real contact area. In the real contact area, at first it has a very mild friction, but that heat generates and heat comes in this surface, and then second time contact, third time contact, and then something wrong happens or not. Okay, so understanding about the phenomena in this phenomena, we need to make a much more larger system. So we need to coarse grain the solid materials. All right, so this is some example to make some coarse grain particle of the metals, but we make this second time coarse grain. First coarse grain and second coarse grain. Then after that, we use some equation of motion. And if you are interested in also this paper describes much more precise method. So, but finally, we can have this kind of very basic concept model. Okay, here we put some SPH particles, and here's some other particles. And then in this red and blue part on the layer 3 and 4, so we calculate the dissipation force and Tomlinson force and some interface interaction like this. And then we have some friction. And here you can see that so load dependence can be so these kind of phenomena is obtained by experiments, and then we can reproduce it by here. And then here's another one is that heat generation, temperature. So the part 1, 2, 3, 4, the heat generates here, and then it goes to another part, and it diffusion occurs, heat diffusion occurs, and then another part, the temperature rises, the third part and fourth part rises. So this means that so we can correctly calculate the force heat generation and heat diffusion and some fluid motion. Okay, and in this case, bottom-up simulation can do the surface interaction between this kind of three materials. We calculate some molecular dynamics simulation and calculate the force interaction correctly, and then have some. We just want to obtain some between the force reaction parameter by like this red line, okay? And then we put this red line to this kind of SPH simulator, and then we could reproduce some friction, okay? And this method is extended to the DEM and the SPH. And we sometimes we put some particles here and for the lubrication, and then we rub here, and then some this is a change of the friction coefficient with adding some oxides. And we put some here, and we can reproduce the sequence of the material difference by this simulation. All right, but the last topic is about the much more wear and much more scissoring and much more heavy condition. Okay, so in this part, in this simulation, we only use the elastic interaction. Okay, but many materials have elastic plastic interaction. So in the heavy condition, so they move to the not only for the elastic, but they move to the plastic condition, and then the surface so structure changes, and then friction occurs. So Dr. Sugimura-san made a bottom-up concept to simulate from the including the elastic plastic information feature to the this kind of SPH particles. So this is one feature. And then here shows the temperature difference. And here, so we are rubbing alumina and titanium. And then you can see that alumina, so heat conduction is very good. So heat goes to every other part. So this is picking some temperature of the sliding surface, okay? So heat can easily dissipate in this way. But in the titanium, so heat conduction is not so good. So the temperature you know, the heat energy remains on the surface. So it goes like this red line, okay? Red place remains after the this sliding like this. On the other hand, so titanium is much more elastic, much more hard material, and this is much more alumina is much more soft material. So this is elastic or plastic. If it is the going to the elastic part, it is we put some red sign, and in the titanium is elastic, and this is alumina is plastic. So we can distinguish the what's happening on the some real contact area, including the heat dissipation and heat conduction and so on. And so in the very classic experimental experiments, the professor in the UK said, this kind of temperature rising is the hot spot or the yes and so on flash temperature, and they call it. And flash temperature can be described in the theoretical point of view, like using this kind of simulator. And but you know, but this kind of surface roughness is not it's very artificial, and in realistic system is like this, and we extended this. And one more thing is that we made some sphere particle to coin-like particle. Using the coin-like particle is that lubrication occurs in the very this kind of anisotropic system. Means that in the sliding direction, it is much more larger, and but in the this side, it's not. We need not so many length. So the length scale between the this side and this side is different. So we made some coin-like structure, and then here's some basics. So temperature rises in the real contact area can be simulated using this new simulation technique. All right, so this is almost a conclusion. So multi-physics simulation is developed to analyze the motion of polymer from this kind of metal and polymer and so on. And then we can reproduce and model the heat generation and heat conduction in the real contact area. All right, so I'd like to end, but before ending that, so I'd like to express that. So we have in 2027, we have a large conference in the Himeji city, which we are in the Hyogo prefecture. And then maybe you are in the Fukuoka, and in the Himeji, we have a very new convention center, which opened in 2021. And 1,000 people, including half are the foreigners and half are Japanese, are coming here to join. And here in the Himeji area, so the last one was done in the 2023, and many professors in the Kyushu University made effort. And next time we make effort. And so in the Hyogo Prefecture, if you are not interested in tribology, please come to here, because there's an origin of the Japanese beef named Kobe beef, you know, the Wagyu. 97% of the Wagyu is made in Hyogo Prefecture and then go to other place and grew up in other prefecture. Okay, and one more thing is the origin of Japanese sake is also here, and seafoods are very good, and world heritage are good, and the origin of Japan made Awashi Island located in our prefecture. Okay, so please visit Hyogo. Thank you, and let's discuss the origin of the friction. And my picture of the laboratory is here, but we have many collaborators in the the other companies. Engineers are here, and so we cannot take a picture on whole our members. Okay, so thank you for hearing. So I'm very sorry. Yeah, I'm very sorry for talking very fast, because I don't know what kind of part are you interested in. So if you have some question, please. It is very. I'm very happy to have your question. So thank you so much.
Thank you very much. Washizu Sensei, thank you very much. Very excellent talk and very educational. We could learn a lot of topics, diverse topics about multi-scale simulation in the field of tribology. So, unfortunately, the schedule will be behind, and the already past schedule time. But if there are some questions, we would like to have one or two questions. So if you have a question, please raise your hand. Use the raise the hand button. Any questions? Yeah, Professor Kubota, please.
Thank you very much.
Yep.
Sorry, Sensei, thank you very much.
Yep.
Thank you very much, Washizu Sensei. Today, I have learned a lot of things about the great potential for the simulation for tribological phenomena. My question is concerned about catalytic action under extreme conditions. I believe that the contact surface is subjected to ultra-high contact pressure, where the surface can cause plastic deformation. So, in this context, how do you think contact pressure and plastic deformation affect the catalytic action of the surface?
Yes, I think, so I didn't do such kind of simulation, so I cannot answer correctly, but I believe, yes, Kubota Sensei's suspicion, yeah. And so we confirmed the Hertzian contact in the theory, compare the theory and simulation by this method. Yes, and we can reproduce the Hertzian contact. But in this, so we can add some other effect, like the surface interaction much more precisely. And we can also include some fluid molecules, fluid particles here. So if we introduce this kind of fluid particle correctly, we can discuss about the capillary. Yes.
Okay, thank you very much.
Thank you.
Thank you very much. So if we think of if you can include some asperities, so surface roughness, maybe the contact pressure become quite high at the top of the asperities. So maybe in that case, there are some different phenomena compared with the relatively low contact pressure surface. How maybe?
Yes, exactly. I think so. Yes.
Okay. So any other questions? Tanaka-san, please. Yes, please.
Yes. Can I hear me? Thank you so much for your very, very nice talk. And I'm very interested in grease lubrication. And as you know, grease lubrication has a very, very wide range of distance in vertical direction and also horizontal direction. Do you have any course grading method applied to this phenomena? And also, how do you think this wide range of the distance in your calculation?
Yes, yes. Very good question. Thank you. And so in this simulator, the size of the particle can be varied. The smallest size is the united atom, means that CH2 is one particle, okay? And the middle and the large. So in order to, because this is a coarse grain model, so the size of this particle is not limited. Okay, so if you want to simulate the whole share, maybe we can coarse grain to this size, and then if we want to understand this size phenomena, maybe the middle particle can be used. So we can vary the model to focus on which phenomena we'd like to understand. But whole phenomena in one simulation is difficult, I think. Yes.
Thank you. I understand. Thank you so much.
Okay. So any other questions from audience? Yes. Professor Yagi, please. Yagi 先生、どうぞ。
Can you hear me?
Yes. Thank you.
Okay. Thank you very much for nice presentation, Professor Washizu. For SPH simulations, it seems to be very suitable for dealing with large-scale phenomena. But in your simulation, asperity contact, I think that there are many complicated phenomena in grain structure, phase transformation, and breakdown of grain structure. Do you have any plan and idea how you consider phase transformation and the change in size of grain structure and so on?
Yes. One thing is that so the torsional, I mean some tensor-like effect is already introduced in this model. So this tensor-like deformation can be included, but now in our present model we don't introduce a multi-grain system. I think we can theoretically we can introduce this by combining the SPH combining some phase transition effect using some other equation of motion like I forgot some other maybe using in other metal science. Yes. So grain boundary and formation of grain and so on can be extended in future, but not. It is, I think, it's difficult in near future.
Yeah, very difficult.
Yes. But I think it is possible in the future. Yes.
Okay, thank you very much.
It's okay. So, any other questions from audience or comments? So, I'm sorry, the time is already passed. So, I would like to close this seminar now. But if you have further questions, maybe you can send email. Maybe in the webinar poster, you can find the email address or of I'm not sure. I'm sorry. If you do have a further question, please contact I²CNER office, and probably they will transfer the question to the Washizu sensei. So, Washizu sensei, Professor Ashida, thank you very much again, and hope to see you again soon.
Thank you.
And also, all the attendees, thank you very much for joining this seminar. We hope to see you again in the next seminar. Thank you very much.
Thank you very much.